Hello.
Yes, sir. Hello, sir.
Yeah. Okay. Fine. So I hope you can see my tablet, right? Okay. So actually, this is how we used to conduct all lectures till last year, when because of lockdown we could not meet. So probably this is a new experience for you, but I think most students are comfortable with this as well. So I actually didn't plan anything for today so far. What should we do? So I was scanning the previous RMO papers to see if any of those questions can be useful for you to practice. So there are some which we can share and discuss today, but in general, I feel that the older RMO papers are anyway quite easy compared to what we expect these days. So I mean, it's only going to be limited amount of practice that you will get from only RMO papers, at least past RMO papers. So maybe at some point we will also start looking at some easy problems from other sources. So maybe some easy INMO questions which I will pick out and share for you. Because quite frankly, some of the older INMO questions could be as difficult as today's RMO. Okay, so yeah, it is fine to use that as practice. Okay, so I'll cherry pick some few questions out of older papers and share them with you. So I'll do the same now also. So I'll just give me 1 minute. I'll copy a couple of questions and I'll give you some time to think, and after that we can start to discuss. Okay. So yeah. But apart from that, you are welcome to go through all the older RNA papers and see if any of them you find to be useful, or any particular question which you find that it is worth discussing. We can always do that. But yeah, not necessary to be done. Okay. So I hope you can see the screen. So these all three questions are from INMO 2004. Okay. So actually, I copy pasted them from the paper because the ones which I had also had solutions written below that. So I didn't want to reveal that. So I'll give you some time to think about this question. So, can you raise your hand once you solve question one? Okay, let me just draw the diagram of question one. But I think for those who have solved it, I think you can agree that it is not difficult. It is basic application of things such as congruent triangles and things like that. Right. So, I'll draw it roughly as a square, but not exactly. So the before applying the given information, do we know anything about these points already based on standard results of quadrilaterals?
Sir, it is a parallelogram, KLN.
Yes, it's a parallelogram, right? And the reason is that if you take these triangles, right? If I join one diagonal, for example, if I join AC, then I can apply midpoint theorem in both sides, and basically what I'll get is KL is parallel and half of AC, and MN is also parallel and half of AC. And therefore, what I get is that this is a parallelogram. And so this is true for any quadrilateral. Nothing special about the given information. If you join the midpoints, you are always going to get a quadrilateral parallelogram. And one more way to characterize a parallelogram is, of course, that the diagonals bisect each other, right? So I could say the same thing in a different way by just joining. I don't even have to join the four sides. I can just join the diagonals, and I know that they will have the common midpoint. So, so this is already good information because what is given to us is also related to this. That what is given to us is that line BD, right? BD bisects KM at Q. So whatever is the midpoint of KM, this is also the midpoint of BD. So not only that, which means that these 3 points are collinear, but also that the lengths are equal. And then further, what is given? The second condition that if I join Q to all, so now at this point, I don't know whether this QA and QC are the straight line or not. The diagram it looks like, but we cannot assume that. We can assume that this is a straight line, but these could be two broken pieces of non-collinear points. But whether or not it's a straight line doesn't matter because we still know that the lengths are equal. Okay, so looking at this diagram, do you see that there are a lot of congruent triangles getting formed everywhere? Okay, so if we use all those congruent triangles, just using the first two conditions from the given question, what are we able to deduce about this quadrilateral ABC?
It's cyclic.
Cyclic house?
Q is equidistant from all points.
Oh yes, of course. So yeah, you can draw a circle with center Q and it will pass through all the 4 points. That is correct.
Sir, also we have that the BD is diameter.
BD will have to be the diameter of that circle. Okay, correct.
Yes. So we get A equals C equals 90.
Yes, correct. So we can say that ABCD are cyclic or diameters BD. Okay, that is also valid. So I would like us to see if we can establish that ABCD is a rectangle based on this information. Do you see that we should be able to do that? We cannot deduce that it is a square just yet, but we can deduce that it is a rectangle. And just to motivate that point, let me draw ABCD like a rectangle. So that we say that whatever you're seeing so far is true in any rectangle. So if ABCD looks like this, and again, so far we still not established whether AQ and CQ are collinear or not. But can you think of a reason why they have to be collinear now? So what is known is that these four lengths are equal. And most important thing, the original information of the points KLMN is still not utilized. We are only using the point Q, but we have KLMN, which are the midpoints of the side. And more importantly, the KM and LN, those two also pass through that same midpoint, the center Q. So how do we use that information?
Sir, angle CMQ will be 90 degrees.
Angle CMQ will be 90 degrees. Yes, correct. Why is that?
Because it should be perpendicular bisector of line CD as it passes through the center.
Yes, correct. Or yeah, exactly. So, or in other words, we can also see that we have lots of isosceles triangles, right? So, as CQD, BQA, these are all isosceles triangles. And for isosceles triangles, we are joining the midpoint of one side. So, I think we can conclude that all these fit of are 90 degrees, right? At all the 4 points.
And so therefore angle KBC equal to 90 degrees as KQM are collinear.
Angle KBC is 90 degrees, correct? Because yeah, basically if I look at the quadrilateral form by these 4 points, then out of those I know three angles are 90 degrees, so the fourth angle also has to be 90 degrees. Okay? So so angles, therefore I can say that quadrilateral KBCM is a rectangle, and therefore now in the original quadrilateral also now I have three angles which are 90 degrees, right? This angle is this angle, so therefore I can say that ABCD is also rectangle. Okay, and there could be multiple ways to reach this. So no, it's not doesn't have to be the only way. But so basically, what we have established is just using the first two conditions, we can say that the quadrilateral has to be a rectangle. And now all that remains is to be seen that what is the third condition adding. So the third condition is LK upon LM equal to CD upon CB. But I mean, I think that directly gives us what we wanted because in a rectangle, we know that this LK and LM, these are going to be equal. So LK will be equal to LM in a rectangle. So therefore it implies CD is equal to CB. And so that is sufficient to conclude that this is a square. Okay, I hope this is clear. So I mean, do you see that this was INMO 2004? I think this was my INMO, my second, first or second, I don't remember whether this was the first paper I gave or second one. But I think I was in 8th standard when I gave this paper. And this question one was the only question I got from the whole paper. So I couldn't do anything else. But yeah, this was the one question I remember. That's like my first INMO question. So I finished this in half an hour, and then for 3.5 hours I was just sitting there because I couldn't do anything else. But you see, I mean, for us today, it doesn't seem that difficult. So the standards of Olympiads have definitely changed over the years. So I mean, try to learn what you can from this problem. Just that be aware of the basics. There is nothing more to it. The basic observation about K and M being a parallelogram, and then Q being the center. So I mean, everything follows from that. There is nothing more than that in this question. Okay. So I mean, you can easily expect. I mean, maybe somebody can say that for even RMO today, this is simple. You may expect this at pre-RMI today, maybe. Okay, but anyway, this is what we had. And just as usual, before we move on, just trying to think about how can you modify this problem, how to generalize this problem. One thing to note is that uh, this is a universal principle in the sense that, so in a triangle, right? In a triangle, how many pieces of information do you need to uniquely establish the triangle?
3.
Three, right? So I mean either three sides or two sides and one angle. Of course, I mean if I give you three angles, that does not work. But in general, three correctly chosen, I should say, correctly chosen pieces of information will uniquely define a triangle. And so what about the quadrilateral? I will thought about this. So you
5.
may be tempted to
5.
say five, right? I mean, there is no such thing as SS test. If you have four sides of a quadrilateral equal to another four sides, there can be infinitely many such quadrilaterals. But if you have four sides and one angle, then it works. So now just go and look at the problem again and see whether we are being really given five pieces of information or not. Because if not, then this problem should be technically impossible. So, and going back to the question, how much information has been given to us? So, I mean, to some extent, I would say there is extra information. I could easily eliminate some of the information and still get a valid problem. I mean, now if I just count that how much information is given, so I think so. This is how I break it down. So the first condition which is given, it's actually combining two things because first it says that B, Q, and D are collinear and BQ equal to QD. So these are two separate things which are combined in a single condition. Then second condition which says QA is equal to QB, QB is equal to QC, and QC equal to QD. So already at this point we have five pieces of information. But those on their own were not sufficient to establish that it is a square because some of it could be redundant. And then after that, the third piece of information was that ratio, LK upon LN. So as the if you ask me, this problem is over-defined. So you could probably eliminate one condition out of these, but not more than one. So this is your exercise. Can you see how you can eliminate some one condition out of this and still be able to define the problem? But if you try to eliminate two conditions, then at least I think the problem cannot be solved. So it is just on the edge of that. Okay. And you'll find this to be the case of A. For example, even last time we had looked at one question about prove that some ABC is an equilateral triangle. If you observe carefully, actually there were three pieces of information given there also. Okay. And then this is basic logic, right? So if you have three variables, right? If you require three to find the values of three variables, you require three equations. Okay, that is how things generally work. So this is a very important one. That this is how things generally work. But there are special cases where you can extract seemingly more information out of less number of equations. Does anybody know any example of this kind of a thing? Where you may have only one equation, but based on that one equation, you can establish the information about three variables. And I'm bringing this particularly to your notation attention because actually this is a common trick used by problem setters. That this is how they disguise information sometimes. So you should be aware of this idea. So how about this equation? So given x, y, z as real numbers and given that x minus 1 square plus y minus 2 square plus z minus 3 square is equal to 0.
They all will be 0.
Yeah, exactly.
Squares will be 0.
Yes. So do you know the values of x, y, z?
X is 1, Y is 2, and Z is 3.
Yes. Okay. So do you see the point that there can be special circumstances under which one equation can give you the values of three variables. But in general, I mean, in this question itself, instead of real, if I said complex numbers, immediately this is not true, right? As soon as they are complex numbers, then there are lots of possibilities to be considered. But because of the special case of real numbers, there was only one possible solution. But be aware of this trick that sometimes you can uh, seemingly there is less information, but whatever information is given is sufficient to deduce the desired output. Okay. So, I mean, going back to the original problem, there could be some special circumstance under which less than five pieces of information could give you that ABCD is a square, but in general, that won't happen. So, I mean, try to construct a problem of your own. Why don't you try to construct some condition under which some ABCD is a pentagon, regular pentagon, or something like that. Okay, just give it a try. There are lots of ideas that way. Because actually, this seems to be a very popular theme that regular polygons they seem to occur in even pre-RMO, RMO many times. Okay. Okay, then we can go to question 5.
Sir, I have a solution for question 6.
Questions. Okay. Can you type it in the chat so that I will take a look at it?
Sir, then can I send it to you?
Yeah. Okay, that's also fine. Yes, that's it. Correct. Actually, Hardik, I didn't understand the last step. When you say 9 ways to factorize, can you list them out? Because I think there also you might get even number.
Okay, sir.
Because we have 900 as 9 factors, but we are talking about pairs, right? And they are not symmetric. So, like 1 into 100 is different from 100 into 1.
Yes, sir. I included that.
Okay. Okay. Yeah, that is correct. Okay, but before that, what about question 5? Anybody has solved it already?
Sir, can you give more 2 minutes?
Yeah, yeah, take your time. So just thinking aloud about this question, not going to give the answer immediately, but so what is the set T? Is it a finite set or infinite set? Because if you have one possible solution of that equation, can I generate one more solution? Yes, correct. I just multiply everything by some constant like k square or something like that. So clearly the set T is infinite and we have to find the GCD of an infinite set. So it sounds like it is a very daunting task that how do we find the GCD of an infinite set of elements. But if you think about it, GCD is very convenient tool, right? Because it is something you are expected to find some factor which will divide all the terms of that entire infinite set. So in one contradiction is sufficient. Like for example, if somebody feels that the GCD should have a factor of 7, but somebody can construct a solution of ABCDEF which is not divisible by 7, then you can be sure that 7 will not be in that GCD because we have found one solution. So to find that GCD, like what is the smallest possible GCD that can be there. Maybe first thing is you have to let us try to find the smallest possible solution of that equation. So has anybody tried to do that? That are able to find at least one possible solution of this equation? And naturally, if you want to find a solution, you will try small numbers. Right? You will not start with 10 or 20. You start with all ones maybe and make small adjustments starting from all A, B, C, D, E all as one and try to make small adjustments till you get one solution. Okay, so if you have not done that already, I'll give you a couple of minutes to try that. Okay, so that is the first thing that once you find one solution of this equation, so then you know one term in that capital set T. And then whatever that solution is, whatever that number you get, A, B, C, D, E, F product, you know that the GCD has to be a divisor of that product, right? And now that puts a certain limit that what are the possible values of the GCD becomes a very small set suddenly. And then after that, you have to continue to think that out of those elements, which can be the GCD, which cannot be the GCD. Okay. So those who have raised their hand, did you find that first solution?
No, but I found the solution to the problem.
Okay, okay, that is fine. But I feel that finding one solution is also important because if you are claiming that whatever number you found is the GCD of that set T, shouldn't we check whether the set T is empty or non-empty? So just to establish that the set T is not empty, it may be worth finding one solution. Yes, Tarini.
Sir, I found one solution to this. So A B C D E F is 1 1 1 2 3 4.
Yes, sir. And I think this is probably the smallest solution. I don't know. At least to try and error, I'm not able to find a solution even smaller than this. So yes. I mean, just to indicate how you can do this systematically. So you can start with, let us say you try all ones. Okay, 1 plus 1 plus 1 plus 1 is 5. Clearly, this is not going to work. So the natural thing what we'll try to do is let us keep all the first ones as one only, and let us keep changing the last element. Okay. So if I change this to 4, you get, and I will quickly realize that this will never work because what we are trying to say here is that because I can group all the previous four ones as a 4. So 4 plus a perfect square is another perfect square. But we know that there won't be any two perfect squares with a distance of 4 between them, right? So I mean that is established because of positive integers. So clearly this series won't work. It will never give a solution. So we cannot have 4 ones. So the next best thing we can do, let us have 3 ones. So 3 terms as 1. Then the other term is the smallest possible length is not a 1, it's 4. And so now you try with this. So 1 plus 1 plus 1 plus 4. And so this doesn't work. And then the next one works. Okay. So like very systematically you can do the trial and error and get the solution as 1 plus 1 plus 1, 2, 3, 4. Okay. So basically, if this is a valid solution, so then what can we say that this is the one element guaranteed to be in the capital set T, which is the product, right? So 24. So let us say if the GCD or the desired GCD is denoted by capital G, then what can we say for sure? That because 24 belongs to the set T, therefore G has to be a divisor of 24, right? So do you see this already eliminates lots of possibilities that GCD cannot be 7 or 15 or so many numbers. So the only possible candidates are the divisors of GCD of 24. So that is a good beginning, but still there are so many candidates. Like what are we claiming exactly? That, for example, 24 has so many factors. Suppose somebody says that the GCD is 3. Suppose somebody claims this. Then to establish this claim, what they'll have to prove is that every possible solution of that equation will have GCD 3. And not only that, this there exists some solution for which this product ABCD is F is actually equal to 3. Otherwise, I mean, there can be a larger GCD, right? So whatever is your claim, you have to prove that every possible solution of ABCDEF will that product will be divisible by that particular GCD. So for those who have found the solution, what is the GCD that you are claiming?
24.
24. Okay.
24.
So the claim is that GCD is 24. So now what we need to prove that if I give any 6 tuple which satisfies that equation, then what should happen? That's the product A, B, C, D, E, F, which will belong to the set T, but this should also be a multiple of 24. So this is what you have to prove now. And if you prove that, then that will mean that 24 will indeed divide every possible term in that capital set T. So despite that set being infinite, we can be sure that every term will be divisible by 24. Okay. So this is what we need to do now. And of course, 24 can be broken down into 3 and 8. So you can separately try to show that 3 has to divide the product and 8 has to divide the product. Okay. And so at this point, see, one more very important thing which has happened is that you have broken the problem purely into a question of remainders. Now that original equation may look very complex, and finding the set of all solutions for that original equation is probably a very difficult task, if not impossible also. But we don't have to concern ourselves about that. We only care about the remainders modulo certain finite divisors. So that puts a very good constraint on the problem. So I mean, how do you solve the problem after that is relatively minor detail, but how do you reach this point is very important. Okay, that recognize that what is being asked is not that daunting. Once you find one solution, like once you find one solution 24, you can make an educated guess that maybe 24 is the right answer. And then after that, you just break the problem down into some modulo arithmetic. Okay, so the understand this logical flow, that what we are doing first and what we are doing next. Okay, then proceeding along the next part. So first thing, let us say that part 1 to be proved. So part 1 we need to show that 3 divides this product. So how will you continue this proof? Yes, Raghav.
So you just take mod 3 of the whole equation, and you assume that 3 does not divide any of A, B, C, D, E, F.
Yes.
Then that gives you that F square is congruent to 5 mod 3.
Yes.
This is a contradiction.
Yes. Correct. So I mean, for that the prerequisite is that just as we are all familiar with multiplication tables, right? We know that 7 8s are 56, for example. That is something we inculcated very early. So in the same way, this table of squares modulo various divisors, that is a very important information that we should all carry just like that. We should have to compute that every time. So like common divisors up to 10. Okay, so for example, what are the possible remainders modulo 2, modulo 3, modulo 4, modulo 5, etc. Okay. So all of these, what are the possible remainders when you divide a perfect square modulo up to modulo 10? And similarly for cubes also. Cubes, I mean, I still don't remember, but if possible, at least try to remember the first few cubes. So let's say modulo 6. Okay. So this is a very basic information that you should remember like a multiplication table, and that will quickly save you a lot of time. So in this case, particularly what we would like to use is the modulo 3. That if I have a perfect square, if the number is divisible by 3, then of course its square is also divisible by 3. But if the number is not divisible by 3, then its perfect square leaves the remainder 1 modulo 3, right? So as what Raghu is saying, that we can go by contradiction. If possible, let none of A, B, C, D, E, F be divisible by 3. Then that original equation, right? If I rewrite this modulo 3, I'm just going to write 1 plus 1 plus. So 5 times 1 is congruent to 1 modulo 3. That is what it will be. And that is clearly not possible because you are getting 5 and 1. Okay. So which forces that at least one of all those numbers is divisible by 3. And therefore, then if one of them is divisible by 3, obviously 3 has to divide their product. Okay. So we are almost there. I mean, we have completed more than 50% of the question now. That first was to make the guess that 24 is the answer, then showing the calculation for 3. And now what about 8? So 8 can be a little bit more tricky. So I'll give you some time to think that how do we prove that 8 has to divide the product. So 8 can be a little bit more tricky because 8 is not a prime. 8 is actually a power of a prime. And so like one way to break down the problem is try to go at it step by step. That so that at least one copy of 2 exists in this. Then try to show that at least 2 copies of 2 exist, and then finally show that 3 copies of 2 exist in the prime factorization of this product ABCD. So you can go at it that way, one copy of 2 at a time. I don't know if there is any way to directly show that 8 divides the product. I think it has to be done step by step only. Okay, so I'll give you 2 minutes to try this. Yes, Anushka.
Sir, we can do this the same way we did the other part.
For the 3, the same thing.
Yes.
Okay, so which is the
Yes, the possible remainders for perfect squares for 8 is 0,
Yeah.
1 and 4.
Correct. Okay. Okay. Then what will happen?
Uh, from in A, B, C, D and F, at most one square, A square, B square, C square, and yes, all those squares. So at most one square can have remainder. No, wait, not like.
Yeah, I think going mod 8 at the first step. I mean, first, like if you look at the what you're saying is correct. You have to do it like the previous question. So if you look at the previous part, the first sentence was, if possible, let none of them be divisible by 3. In the same way, what is your first, like proof by contradiction? What is your first claim? That if possible, so that is why what I'm saying, instead of doing this question directly, right? Let us try to do it step by step. Let me first, like part 2A, let me first establish that at least 2 divides ABCD. That can it be that all of them are odd? And can I at least show that the product is even first? So try to solve question 2A. Then 2B, which is 4 divides the product. And then finally 2C is that 8 divides the product. So let us go one level at a time. So those who have solved the entire question, did you do it in somewhat similar lines as this, or you have a completely different approach?
Instead
Same
of a
approach.
slightly different approach, like instead of
Slightly
taking
different.
each copy of two divides, I like consider which ones are how many are even.
I see. Okay. So if you have solved all the three questions, right, you can look at the remaining problems from that INMO paper. But more or less, some of the questions are good. I mean, they're not very easy, but that is one way of practicing further. Do you have the INMO papers, or if you want, I can share them with you. I should have a PDF.
We'll take it from the net.
Yeah. Okay.
Thank you, sir.
Okay, so let us see how to do this step by step. So first, we want to prove that 2 divides ABCD. So this is where Anushka, what you were saying, we can try that approach. Let us claim that if possible, let none of ABCDEF be divisible by 2, because that is the only condition under which this will not happen, right? So if they are all odd, in other words, so at first glance, I mean, if I just, so I have to consider what is the modulus under which I would like to get the contradiction. So if I try to say modulo 2, we see there is no problem, right? Because left hand side is odd, right hand side is odd. So modulo 2 will not really help us. So maybe we'll like to try modulo 4. But even modulo 4, you see that it doesn't really help us, because if all the numbers are odd, then we know that the perfect square of an odd number is congruent to 1 modulo 4. So you're still going to get 1, 1, 1, 1, 1, and 1. And so that is 5 congruent to 1 modulo 4. So again, there is no contradiction. So modulo 4 is also not helping. So then let us go to modulo 8. Okay. And this is where very important thing can be useful, that even modulo 8, like an odd number square, is also congruent to 1 modulo 8, no matter which odd number. Okay. So this is a very important observation which can help us to do this problem. And do you see why this is going to be true? Like if I, let us say my odd number looks like 2 times x plus 1 bracket square. So if I expand this, why should that be congruent to 1 modulo 8? So this is clearly looking like 4 times something, right? 4 times something plus 1. So it is congruent to 1 modulo 4, but I'm saying it is 1 modulo 8. So how is that possible? So what is the thing inside the bracket? It is x square plus x, right? Or I can factorize it further as 4 times x into x plus 1 plus 1. Okay. And now do you see why? I mean, this x into x plus 1 will also be even, because either x or x plus 1 of them has to be even, right? So the product has to be even. So I think we can say for sure that this whole thing is of the form 8k plus 1. Okay, so therefore an odd square is also always common to 1 modulo 8. And that is what is going to help us here, because now what I can say, like term by term, every term on the LHS will again will be 1, 1, 1, 1, 1, 1. And also what now I'm claiming is 5 is common to 1 modulo 8, which is a contradiction. Okay, do you follow this? How modulo 2 and 4 did not help, but modulo 8 is able to solve this problem. So therefore, at this point, what we can say is that actually this cannot be true, that all of them odd is not possible. So therefore, at least one of them is even. And now if you think about it, if at least one of them is even, it cannot be that. So can it be that one is even and remaining five are odd? That won't be possible, right? Because the way the thing is set up, like no matter how where you place the even number, like if you say this is even and all these five are odd, that is also contradiction. Or if one of the terms on the left is even and everything else is odd, this is also contradiction. So if at least one of them is even, actually what we can say is that at least two of them have to be even. It cannot be that only one is even and five is odd. So almost like we are trying to show that 2 divides the product, but in that we got an extra bonus that in fact we have two copies of 2 already, right? So do you think that therefore we can say that 4 has to divide the product? So we are very close to the goal. And now from here, what we'd like to show that actually 8 divides the product. So what is the only circumstance in which this is true but this is false? Like you have 2 copies of 2, but we don't have 3 copies of 2. So why will that happen? So the only way that can happen is that the two numbers which are even, right? So even numbers come in two types, right? The numbers which are divisible by 4 also, or the numbers which are divisible by 2 but not by 4, right? So basically even numbers come in the form of either type 4k or 4k plus 2, right? So the two even numbers that we have, if even one of them is of the type 4k, then we will have total 3 copies of 2, right? So the only case that is to be considered or rather eliminated is that both the even numbers are of the type 4k plus 2, right? So at this point, to prove this, we would say that if possible, let both the even numbers that we are getting be of the type 4k plus. Okay, so for example, case one is that, so when we are saying I have two even numbers out of A, B, C, D, E, F, I mean, without loss of generality, A, B, C, D, E can be permuted, but F is a separate case, right? So the first case is that A and F are even, not only even, and of type 4k plus. And case two is that A and B are even, and of type 4. So I need to solve both the cases separately, case one and case two. Okay. And now here again, modulo 8, just as we said that odd number square is common to 1 modulo 8. What can you say about the number of type 4k plus 2 modulo 8? So if I expand this again, just as before, what I'm going to get is 4k square plus, no, sorry, not 4k square, 16k square plus 16k plus 4, right? So do you see this is clearly, I mean, this part is divisible by 8. So this will be basically 4 modulo 8. Okay, so this is a very important classification that perfect square modulo 8, if the number is odd, then the answer is 1. If the number is of the type 4k plus 2, so this is the first kind of even number, then the answer is 4. And if the number is divisible by 4, then of course the answer is 0. Okay, so but not only that, we know what are the remainders of a perfect square modulo 8, but under what condition which remainder gets applied. Okay, so this classification is very important. Okay, so applying that, I think the both cases get simplified very quickly. So case 1. So like if I try to write case 1 over here, where we are saying that A and F are congruent to like type 4k plus 2. So if I write the numbers A, B, C, D, E, F, right? So modulo or rather A square, the squares of all of them. So we are still going with the assumption that everything else is odd, because otherwise we anyway have an extra copy of 2. So these numbers are odd, and this is of the type 4k plus 2, and this is also type 4k plus 2. So therefore, the modulo 8, the remainders are going to be 4, 1, 1, 1, 1, and 4. And so what you're getting is 8 is congruent to 4 modulo 8, which cannot happen. Do you know this symbol that I don't know if it's popular, but when I write this, it means contradiction. Okay, so case 1 gives a contradiction. And what about case 2 also? So case 2 is where I'm assuming that let A and B be of the type 4k plus 2, and everything else is odd. Again, if I take the modulo 8, then this will be 4 plus 4 plus, the rest is all 1. And again, I'm going to get a contradiction here because I'm going to get 3 congruent to 1 modulo 8. Okay, so in both cases, I get a contradiction. So what that means is that it cannot be the case that both of the numbers, like the both even numbers of the type 4k plus 2 is not possible. So therefore, at least one. So therefore, what I can guarantee that exists at least one number of the type 4k and plus another even number. So therefore, total I'm going to get 2 copies of 2 from here and 1 copy of 2 from here, and therefore together they have to divide. Like 8 has to divide ABCD. Okay, so I think there may be even simpler approaches, but I feel this is the most systematic one, where we are adding 1 copy of 2 at a time. So like slow but steady progress in the right direction. But any questions anybody has, or Raghav or anybody else, if you have any different solution, you can explain that.
Sir, I did it in a slightly longer way in some sense.
Okay.
So like what I did was like first you consider that one of ABCD is even, ABCDE is even,
Okay.
and then like you get suppose without loss of generality, suppose A is even, then you get B square plus C square plus D square plus E square will be congruent to 4 mod 8.
Okay. Okay.
Then you get that A square is congruent to 4 mod 8, which means 2 divides A and 4 divides F.
Okay.
So you get 24 divides ABCD here. Then
Okay.
for like 2 of ABCD are even,
Okay. Okay. So basically,
C square
like,
plus D square. Yes, sir.
got it. Got it.
But
So basically, you're making
after,
cases in terms of how many terms are even, right?
yes, sir. But after like case 3, like when 3 of ABCD are even, you don't need
Yes.
to do anything because like already if there's
Yeah.
any
Yeah. Yeah.
solution possible, it already divides it. So you
Yes.
don't.
Yes. Once we have found 3, yeah. So basically, the only 2 cases you have to consider is 1 term is even and 2 terms are even.
Yes.
Yeah. Okay. Yeah. That is also fine. Okay, so any approach you follow, as long as you're systematic, you will be sure that all the cases are covered. Okay. So again, I mean, the solution is somewhat long when you write it this way, but actually the process of discovery is kind of you're going naturally from one step to the next step. So there is nothing that is hidden from us as well. Okay, so I hope everybody has followed the question. So going back to the very beginning, that how this whole question got started. So the first step was to find one solution of that original equation, that what is given to us. So once we find that one solution, then we know one element of the capital set T, and that immediately puts a upper bound on what are the possible values of the GCD. And so once that we found one solution where the value is 24, so then we made the claim that let G be equal to 24. And then to prove that claim, we had to separately prove that no matter which solution of the original equation you consider, that the product ABCDEF has to be divisible by 3 and 8 separately. And then once we have established that, so the out of that, the 3 part was more trivial because they're like 3 being a prime number and in one step it was finished. But for the 8, we have to have a more systematic approach. Like the idea of adding one copy of a prime number at a time is going to be very useful for us. So just to motivate this idea, I'll give you one more question as practice. I will not solve it right now, but actually this is a kind of a question of the same theme where you have to consider not just a prime number but powers of prime numbers. So let me just pull that question. So did we do this question? I don't remember. Okay, RMO 2009 question 2. This is familiar to you, or maybe I'm remembering from somewhere else. But if not, you'll see that this question is also very similar kind because 289 is 17 square. So you have to do it in two steps. One is like divisibility by 17 and then divisibility by 17 square. So it requires a two-step approach as well. Okay, so anyway, try this problem at home, question 2, and you will see that similar idea can be useful in other questions also. Okay, then with that, so that finishes the discussion of question 5. Question 6, I'll leave it as a homework for you because it is kind of, you see, in some sense, I even consider question 5 as a kind of trick question. That it seems that what the question is asking is very complicated. Like it's a very complicated equation for which you have to find all solutions, and then once you find all the solutions, then find the product and then find the GCD. But really, what was required to be done was very simple. So we have to bypass lots of steps. In the same way, question 6 may look like you have to find all the solutions, and then once you find that entire set, then you count it, and then that number will turn out to be odd. But actually, if you think about it, the concept of odd and even is just about pairing. So if you find the right matching of the solutions, you can finish the problem in much simpler approach. Okay. So with that hint, I would like you to try question 6 at home. Okay. I don't want to do that right now. So right now I want to do something else, which I would have. So Pranav, you are here, right? So you are trying to construct real numbers, and so I thought that why don't we try to learn something about constructing numbers. So what is this whole business of constructing numbers? And I mean, maybe it's a kind of philosophical question that what does it even mean to construct a number? It is not like they're all like imaginary things, right? So it is not like you have to take the actual building material and start constructing something. So what do you even mean by constructing numbers? Okay, uh, so let's try to talk about that. Okay. And yeah, before that, just want to indicate that what you can do, as I already said, you can go back and look at the entire INMO 2004 paper. So the remaining 3 questions also you can try to solve. And at least, mostly speaking, the like older INMO papers are easier than these days. So you should be able to solve them. But if you get stuck, you can always ask me, or you can put a doubt on the WhatsApp group so others can help you. So do make good use of the WhatsApp group to communicate the problems that you're trying to solve. Okay. But apart from that, I will also send you some additional questions for practice for next time. Okay. So now coming to this topic of constructing numbers. Okay. So the idea of constructing numbers in any way is that, I mean, it comes down to the basics of how mathematics is constructed in the first place. That if you understand how mathematics like geometry is built, like you have things like axioms, right? So you assume some axioms about point and line and maybe some basic properties, and using those axioms, you are able to construct or prove more complicated things such as Pythagoras theorem or Heron's formula and things like that. So this whole idea of using some axioms and using those axioms to construct another object. This is the bedrock of how mathematics is developed. And one important principle we try to use this is that you would like to make as few assumptions as possible, right? See, if we can have a system where only 5 axioms are sufficient, why would we try to go for a system where we require 100 axioms? So we'll always have to try to use the least number of assumptions and try to derive everything else from that. So in the same way, I mean, we have things such as, natural numbers, rational numbers, real numbers, I forgot, integers, complex numbers. And each set has its own properties. Like for example, we know that for rational numbers, if I have a plus b, if a and b are both rational numbers, then I know that a plus b is equal to b plus a, for example. Or some other property like a times b plus a times c is equal to a times b plus. And so we use all of these properties when we are manipulating rational numbers. And very similar properties are true for every set which I have listed here. So imagine that if we treated each of them as an independent entity, right? Then the natural numbers will have its own set of axioms. Integers will have its own axioms, and similarly, like real numbers will have its own axioms. And so it will be like you are making the copies of the same axiom for every system separately. So like there is a lot of repetition here, that the same property, that a plus b equal to b plus a, you are assuming again and again for different sets of objects. Just because we are, just like magic, we are saying let real numbers exist. So this statement that let real numbers exist, this is the magic statement which is causing all of this problem. But instead of that, if you can show through some systematic way that you can build larger, more complicated objects using simpler objects, and then you'll have to make the least number of axioms to solve everything. Okay, so that is the reason why we would like to construct numbers. And so just to motivate this with a very simple example, let us we can construct natural numbers also using set theory, but that is going one step too far for us right now. So for today, am I going to be assuming that natural numbers exist? Okay. Okay, how they exist, why they exist, we don't care. But for now, our working set of assumptions is the natural numbers and they're all axioms related to addition and multiplication. Okay. So I'm not going to state all of them here, but the standard things like the commutativity, associativity, and those kind of things. Okay. So these are all the things which are assumptions given to me. Okay. So on the basis of these assumptions, the first task is that can we construct integers? So when I say construct, what I need to define, what do we mean by construct? That, I mean, I'm accustomed to using the symbol like -1, -2, -3. But if I can give a definition to these symbols in terms of some other object, then that is what I call a construction. Okay. So for example, here is one very simple construction of a natural integer. So I can say an integer is an element of the set So you understand this notation? This is a cross product of two sets. So in other words, every element of this set will have two terms, right? A first term and second term, where the first term is a natural number and the second set number belongs to the set 0, 1. So what do you think this 0, 1 indicates?
Sign.
Sign, correct. Yes. So there will be some condition that it is 0 denotes positive sign and 1 denotes negative sign. So as such, I don't have to write -1 or minus 10, for example. Instead of writing -10, I could denote it by 10, 1. So I understand that -10 is 10, 1 and 10 is 10, 0. And now I can, define all the addition operations. Like suppose I have given two integers, right? A1, B1 and A2, B2. I can define the addition on them plus A2, B2 as, like, there will be a whole set of complicated rules, like case wise, that based on which number is positive, which is negative, which is larger, which is smaller. So like some if else cases will be there. But you see it is possible to define addition, right? Of two integers so that I'll get a third integer. So that is what we mean by constructing integers. Okay. Only one slight problem if you look at this construction. You see 0 is not part of this set because 0 is not, 0 will not align with this, right? So we need to make a small change. So along with this n cross 0, union some special set, right? So it can be the empty set or any set which denotes the 0. Okay. So this could be the whole definition of integers. So if I were to use this version of integers, maybe somebody, like, we are accustomed to write like -3 plus 5 is equal to 2. But using this complicated system, we're going to write as 3, 1 plus 5, 0 is equal to 2, 0. But it is so clumsy to write, and that is the only reason why I use this -3 and like symbols. But technically, it is possible to define the symbols -3 and +5 in terms of natural numbers. So do you see that how we don't have to create a new set of axioms for integers now? Whatever axioms we knew for natural numbers, those and the definition of addition and multiplication, I can infer the axioms for integers. So I don't need a new separate set of axioms for integers. So that is the advantage of constructing numbers in this way. Okay. So basically for now, from natural numbers we are able to reach integers through some way. And of course we are going to abandon this notation. We are not going to keep writing 2, 0, A, B, because we have a much easier way of representing the same information. So now from here we need to go to rational numbers. So can anybody suggest that how can I define this set of rational numbers? And by the way, before going that, observe one very unique thing about this construction of integers is that every integer has only one representation in this system. Otherwise, it would be a big problem, right? If one integer like -10 can be written in two different ways, then I have to again do something to eliminate those extra copies. So having only one representation for every object is a very useful thing. Yes, Kana?
You can define the rationals as a set of ordered triples where the first two elements are relatively prime natural numbers and the third one is the sign.
Oh, yes. Okay. So this can be a set of all ordered pairs of rational numbers A, B, C. So where A and B are both, so you want them to be integers or natural numbers? Natural numbers, right? Because you already have a sign separately.
Yes.
And what about 0? I think you have to include 0 also, right?
Yes.
Okay. So yeah, this could be one way of constructing rational numbers. And so sorry, here I should say A and B are relatively prime numbers. So all such triples of ABC where A and B are co-prime, and in this way we can define rational numbers. There are more elegant ways of defining rational numbers also, and I'll mention them briefly. But I hope everybody agrees that this is a perfectly fine way to uniquely construct rational numbers. And again, if I have a rational number Q1 which is A1, B1, C1, and Q2 which is A2, B2, C2. We have to come up with a whole bunch of complicated rules, but it is possible to define Q1 plus Q2 in some way, right? Like whatever standard way we have. Yes, Raghav.
But instead of working with triplets, can't we just use integers to make a ordered to make ordered pair of for creating rationals like z
Yes,
cross z minus 0?
you could use integers also. So what Raghav is suggesting an alternate definition is let Q be the set of only integers. So A and B are integers, and but they are relatively prime. Or what?
Not necessarily.
So if you don't let relatively prime, then the object 2 comma 4 and 3 comma 6 will both exist in your set. And then which of them is the one which you refer to as half? So your set should
But then
have,
we can create equivalence classes and then show that two numbers in this class are equal if the product is equal.
yes, correct. So the equivalence classes is one idea which I'm going to come to. But yeah, but if you don't do that, then this name definition will not work, right? You cannot just say that A, B are any integers and without caring out whether they are relatively prime or not.
So then I think we come up with the same problem in the previous construction.
Uh, Sorry, what is the
Even
problem?
B1 can be suppose 2 and 4, and then A2, B2 can be 1, 2, and
Yes, correct.
sign
So
can.
yeah, so yeah, correct. No, I mean I think what you were suggesting that A, B be integers and they be relatively prime. So then we won't have a non-co-prime pairs here. So 1 comma 2 will belong to Q, but 2 comma 4 will not belong, right? But here again there is a slight problem of sign, because what about minus 1 comma 2 and minus like 1 comma minus 2? Like they are both referring to minus half, right? So again
Yes.
there is some duplication happening here. So
So that can be taken care by equivalence classes.
yeah, so I mean if you want to invoke equivalence classes anyway, then let us do it in the proper way. Okay, so let me just talk about these equivalence classes. I had referred to this in the one offline lecture which I took, but I don't know if everybody was present for that. And actually, that was kind of one of the motivations for me to discuss this topic in the first place. Okay, so on sets and equivalence classes. So, can you raise your hand if you know these things already? Like, if everybody knows it, then I won't cover it. But if there are anybody who has not heard of this, then I would like to cover it. So, anybody who's already familiar with these ideas? Okay, if not, then yeah, it's a very good topic. Actually. So, relations, functions are very important building blocks of everything else in mathematics. So, you have to spend some time on them. So, at the very basic level, a relation is nothing but, so like, for example, I can denote a relation with the letter capital R, is nothing but a subset of the cross product. Actually, my definition is a little bit vague. Let me refine it. Relation R on any set A is a subset of the cross product. Okay. So in other words, R is a subset of the cross product. So in other words, if I take any elements of let us say small a and small b belong to A, then we can ask the question: does the ordered pair A comma belong to R, or it does not belong to R? So these are the only two possibilities. And if it belongs to R, then we say that A is related to B under R. And if it does not belong, then we say A is not related to B. So, I mean, this is the most generic and somewhat vague definition that so relation can be any association between two elements of that set A. Okay, but if we take specific examples, then it will become clear what is this relation business. And often we denote the if two elements are related, we will denote it by A R B. So we write the relation between them. Okay, so for examples of like typical relations, so let us say the set A we are talking about is the set of let us say real numbers. Actually, that R is confusing. Okay, let us take natural numbers. Okay, and the relation I'm talking about is the less than sign. Okay, so in other words, A less than B is defined as the set of all the okay, not less than sign literally. Let me write the letters LT. Okay, so LT is the name of my relation, which is a set of all ordered pairs of natural numbers such that A is less than B. So, for example, 1 comma 2 is a member of this set. 2 comma 3 is a member of this set. But 2 comma 2 is not a member because equality is not covered. It is strictly less than. So this LT is an example of a relation. So similarly, you see LT, GT, LTE less than or equal to, greater than or equal to. These are all examples of relation. And this currently I'm considering them as relations on the set of natural numbers, but we can easily define them on other set like rational numbers or real numbers. Okay. So can anybody give examples of other relations? What other relations can be considered apart from less than, greater than? What about integers? If I give it two integers, can you think of some property that either that property is true or it is not true? So how about divisibility, for example? So let the consider the set of natural numbers, and let me define the set div as the subset of n cross n. So subset meaning that a and b are both integers, natural numbers, such that a is a divisor of b. Okay, so this is a relation. So basically, any two terms, if the first number is a factor of the second number, so for example, 1 comma 2 is a member of D, and 2 comma 6 is a member of D. But for example, 7 comma 10 is not a member. Okay. So understand that actually when you are familiar with the notation like the vertical bar, like we are comfortable to write 2 bar 6, or even in the previous case, we are comfortable to write 2 less than 3. But just as what we did for integers, that it was very clumsy to write 10 comma minus 1 or 10 comma 0. So instead of that, we wrote minus 10. In the same way, it is very clumsy to write 2 comma 3 belongs to LT. So instead of that, we write 2 less than 3. So in the same way, it is very clumsy to write 2 comma 6 belong to div. But we came up with a shorthand notation 2 divides. But at the back of the mind, understand that what we are saying is whether or not two numbers satisfy the relation or don't satisfy. Okay, and so there can be so many examples of relations of this kind. Important to note that the way this relation idea is defined, it doesn't have to be any nicely behaved equation like divisibility or less than, greater than. It can be completely random. Like if I take any set A I want, like A can be any set 1, 2, 3, 4, 5, 6, for example, and I can just come up with any set of pairs. Like I feel that 1 comma 3 should be related, 3 comma 4 should be related, and 4 comma 2 should be related, and nothing else is related. So this is a new relation which I have defined. This is perfectly fine. So I'm perfectly okay to say that 1 and 3 are related, but maybe 2 and 6 are not related, or something like that. So it's not a very interesting or useful relation, but it is a relation all the same. Okay. So so relation does not have to be well behaved. So I think the word well behaved you may see often. Well behaved means relatively sane, normal object, but that is a special condition that doesn't have to be true for every relation. Obviously, the things such as divisibility, less than, greater than, they are very well behaved, but you can also have crazy relations like that. Okay, so now then the question becomes, if I have any relation on any set, right? What are the properties which I would like to check? So given the relation, and let me use the small letter r for now on a set S. We'd like to check that whether or not following properties exist. So these properties. So there are three basic properties: RST, reflexive, symmetric, and transitive. Okay. So for any relation you consider, you can ask these three questions: that is that relation reflexive, is it symmetric or transitive? And for different relations, the answer may be yes or no, depending on which example we take. So reflexive means that if you take every element is related to itself or not. So for any element belonging to the set, is it true that a comma a belongs is it related? So if every number is related to itself, we call it reflexive. Symmetric means that it has to be mutual. That if one number is related to the second number, then I can also say that the reverse is okay. So it cannot be only one way relation. And transitive means that literally transitive. So if I have three elements, and if it is true that the first two are related and the second two are related, then I can also say that the first and the last one also have to be related. Okay, so this is RST, reflexive, symmetric, and transitive. And so you can ask the question about all the. So if I just make a small table here, and can you fill this that so the less than relation on natural numbers and the divisibility relation on natural numbers. So can you tell me which of this is satisfied by each of these? So is the less than operation reflexive? So in other words, if I take a number like 5, is it true that 5 is less than 5?
No.
No, right? Right. So reflection, if it were less than or equal to, right, then it would be true. But strictly less than, it is not true, correct? So this is not true. What about symmetric? Is if 5 is less than 6, is it true that 6 is also less than 5?
No.
No, right? So symmetric is also not true. What about transitive?
Yes.
It is transitive, right? Because if one number is less than another number, like 1 is less than 2 and 2 is less than 3, so we can conclude that 1 is less than. And this will happen for no matter which numbers you take. So this is clearly, so the less than operation is only transitive, but it is not reflexive or symmetric. Okay. What about divisibility?
It is reflexive, but not symmetric.
It is reflexive, not symmetric. Is it transitive?
Yes.
It is transitive, right? Because if A is a factor of B and B is a factor of C, clearly A is going to be a factor of C. So you see, like every relation will have a different combination that which of these are satisfied, which are not satisfied. Okay. Let us take an example of a number which has a relation which has all three properties satisfied. So let us consider the relation uh, E5. Okay, this is the symbol E5, and again on integers, let's say not natural number this time, it is defined as, so E5 is a set of all ordered pairs of integers such that A and B, or I mean multiple ways of saying that. Basically, I'm going to say that they are congruent modulo 5. So I can say 5 divided the difference, for example. Okay, so any two numbers, we have the same remainder modulo 5, like 1 comma 6 are related, 6 comma 11 is related, 7 comma 12 is related. But let's say, for example, 10 comma 11 is not related. And same with negative numbers also, like minus 3 comma 2 is related. Okay, so this is the basically equivalence modulo 5, like a congruence modulo 5. So now can you fill this table that is this relation reflexive, symmetric, and transitive? Like, is it true that every number is found to itself modulo 5?
Yes, sir.
obviously, like, or in terms of the definition given here. So 5 divides the difference. So like 5 obviously divides a minus a, which is 0. Okay. So it is reflexive. Is it symmetric? So if A is congruent to B, which means A leaves the same remainder as B modulo 5, then is it fair to say that B also leaves the same remainder modulo A, modulo 5? So it is symmetric also. And is it transitive? That if A and B do the same remainder and B and C do the same remainder, then obviously I can say that A and C also will have the same remainder. So you see, this congruence model of 5 is a operation which has all three properties, R, S, and T. And obviously there is nothing special about the number 5. You can take any divisor you want, and based on that divisor, you will get all three relations are true. Okay. So any relation which satisfies all three reflexive, symmetric, and transitive. Such a relation is given a special name. It's called an equivalence relation. Okay. So there is a whole bunch of relations which are equivalence relations. Clearly, based on the example we gave before, these two less than is not an equivalence relation, and divisibility also not an equivalence relation. But this E5, which is congruence modulo 5, is a equivalence relation, and in general, congruence modulo any positive divisor will be an equivalence relation. Okay. So your homework is to try to find examples of equivalence relation. And also note one thing, that we are doing everything here in terms of numbers, integers, but these objects can be any objects. Like for example, if you think about it, similarity between triangles is an equivalence relation. Do you see that if I consider T as a set of all triangles in the plane, and if I define sim as the set of all ordered pairs of triangles, such that T1 is similar to T2. Do you even like just right now thinking about it, do you see that this similarity is an equivalence relation on all the triangles? Because of course every triangle will be similar to itself. If triangle 1 is similar to triangle 2, then triangle 2 is similar to triangle 1. And transitivity also, right? If triangle 1 is similar to triangle 2 and triangle 2 is similar to triangle 3, then triangle 1 is similar to triangle 3. So you understand that these ideas are very broad. They are applicable to so many domains in mathematics, not just algebra or number theory. Okay. So this is your homework. Try to find more examples of equivalence relations from different domains, not just number theory. Okay. So what is the point of defining this equivalence relation? And so that is what Raghav was referring to, the idea of equivalence classes. Okay. So what happens is that if we have a relation, let us say if R, let me switch to capital R, is an equivalence relation on some set S. Okay. Then what it means is we can partition set S into subsets. Let me call the subset S1. And here I'm calling it S1, S2, S3, but in reality they can be indexed by some any other element also. So the motivation for this partition is that I'm going to group all the elements together which are related to each other. Okay, so basically I'm going to create this kind of bubbles S1, S2, S3. So each subset of the original set is such that they are all related to each other. So you can pick any two elements of this set S1, they will be related to each other. You can pick any two elements of the set S2, they will be related to each other, but there will not be any cross relation. So there will not be any connection from one set to the other set. So I can partition my original set into a union of all these sets. Yes. Okay. And then each of these is called an equivalence class. So all of them are called equivalence classes. Okay. So just to go with the example of E5, like the congruence module of 5. So the set of the original universal set is the set of integers, And the relation that you are considering is E5, right? Congruence modulus 5. So can you tell me what are the partitions of these integers such that within each partition all the elements are related to each other? So what will those partitions look like? So for example, if you take the element 0, right, it will belong to some partition. So what will be the other elements of that particular partition?
All numbers divisible by 5.
Correct? Or all numbers is the remainder of 0 modulo 5. And that includes negative numbers also. So this will be the partition 1, P1, or let me call it P0. So do you see in the same way I can construct P1, P2, P3, P4. So this entire set Z will get broken into this partition. So the partition 1 is the all the numbers is the remainder of 1. Then this will be like minus 3, comma 2, comma 7. Should be minus. So do you see that every number of the original set will be absorbed in one of these partitions? So all the partitions are disjoint. That is, I mean, the definition of partitions. All partitions are disjoint. If I take any two elements belonging to the same partition, right, Pi, then I can guarantee that X and Y are related under whatever is the operation we are talking about, like E5. Like pick any partition and pick any two elements like 4 and 14. Then are they related with the relation? Yes, because they are congruent modulo 5 or 5 divided their difference. And in the same way, if I pick across the boundary, like if I pick any element of one partition and any element of another partition, can I guarantee that they will not be related? Because the way the equivalence class thing works, right? Like all the elements related to it are already in this partition. So outside of this partition, there cannot be any other element which is equivalent to it or related to it. Okay, so whenever you have an equivalence relation, you get equivalence classes. And this is a very important concept. And I mean, just trying to visualize that again to go with the triangle example, right? When we said that let T is a set of all triangles in the plane. Sorry, my handwriting is not very good, right? And we said similarity is the operation of two triangles that are similar if and only they are similar. So under this operation, do you see that the whole set of triangles will get divided into this kind of equivalence classes, where all the triangles which are related to each other will go into one bucket. So for example, you could have one very small triangle, large triangle, very large triangle. Maybe same triangle rotated clockwise, anti-clockwise, the mirror image of that triangle. So these are all related. These are all triangles of one particular shape. Another bucket will have a different shape, maybe very elongated triangle. A third bucket may have one particular shape like obtuse angle triangle of a particular angle. So like that, you see there will be infinitely many such buckets created, one for each shape of a triangle. Pick no matter which triangle shape you pick, it will go to one bucket, and in that bucket, all the triangles of the same shape will be contained. And together, the union of all of these buckets will be the set of all the triangles in the plane. Okay, so you can imagine that this is a very abstract concept. Like we are talking about infinite set of infinite objects in some sense, but it is a very useful idea. Okay. So the question is, what is all of this got to do with our question of defining rational numbers? Okay. So we need to return to that question of defining rational. Okay. So consider what I'm going to write now. So let consider the set Z cross Z. So this is the set of all ordered pairs of all integers. No conditions. So every possible pair of ordered integers is allowed. Okay. And now consider this relation. I don't know what symbol to use for this relation. Symbol to use. Let me just denote with a small e. Okay. So small e is a relation on this Z cross Z, and it is defined in this way that so given, let us say I'm given the pair A1 comma B1 and A2 comma B2, which both belong to Z cross Z. So I have to answer the question whether or not these two pairs are related. So I define my relation in this way that we say that these two pairs are related. Okay, let me use the symbol, like the similarity symbol. Okay, instead of writing the E, I'll just write the E, the similarity symbol. Okay. If and only if. So Raghav, can you suggest what should be the condition?
Yes, sir. It should be A1 B2 equals A2 B1.
Correct. So only if this product, like cross product, is identical, then we say that these two pairs of real number integers are related to each other. Okay. So
So
we are almost
also,
out of. Yes, go ahead.
I think the second Z should be Z minus 0 in Z cross Z.
Okay.
It should be Z minus 0 instead of Z. The
Yeah, I
first
also.
line. The first line.
Yeah, I mean, I understand what you're saying, but I'm just trying to see. Let me do that correction at the last minute because I need to be sure whether I need it or not. Like, let me finish the construction, and
Hmm.
then at the end, if we realize we need that, we will do that because we still have to define the equivalence classes and everything, right? So
So
there are
actually,
two.
I think we
Yes.
need that because like suppose if B2 is like 0,
Mm-hmm.
and then that means A1 B2 will always be 0.
Yes.
And then like if A1 and then if A2 is 0, then A2 B2 will be equal to like every number.
Okay. So I understand what you're saying. Correct. Correct. Okay. So what you're saying is we should have it should not be Z cross Z, but Z cross Z except the number 0.
Yes.
Okay.
Otherwise, then if A2 B2 is 0, then A2 B2 will be equal
Yeah.
to every single number.
Yeah. Basically, yeah. Correct. You see the point. Yeah, it's a very subtle point. So yeah, what Raghav is suggesting is that we have to modify this slightly. We cannot have every number match with every number. The second number has to be 0. And you see that intuition comes from the fact that when we have fractions, we cannot allow denominator to be 0. So that is why. So let me denote this by Z star. Just to denote that 0 is excluded. Okay. So Z cross Z star. Okay. So this is the relation that we are defining that if the cross product is equal, then we say that these two pairs are related. So do you see that we are effectively defining what in school we learn as equivalent fractions? Like if you have two fractions that are equivalent, right? We write 9 upon 12 is the same as whatever. What is on the pair? 3, 4, 3, 5, 15 upon 18. No, sorry. 3, 3, 4, 4, 3, oh, sorry, what is the equivalent pair of this? Fine, 20. Sorry. Yes. Sorry, what happened? I don't know. Yeah. So we know this from school, like we call these as equivalent fractions. Do you see that this, if I instead of writing 9, line 12, if I denote this as 9 comma 12 and 15 comma 20, then under this relation that we are defined, it would be perfectly fine for us to say that 9 comma 12 is related to 15 comma 20 because the cross product is equal, right? So what I'm trying to motivate is that, so we are almost out of time, but your homework is to check if is an equivalence relation. Or rather verify. We already know that it is going to be equivalence relation, and therefore, what are its equivalence classes? And you will find that the equivalence classes of this operation is exactly the set of rational numbers that we're talking about. Okay. So the set of equivalence classes of this similarity operation is what we call rational numbers. Okay. So that is the direction which we would like to go. But yeah, we can continue this next time, or I may not even continue this because the only thing was to denote this, show this equivalence classes point. So you will with this be able to reach rational numbers. But for Kano, actually we have to go one step further. We have to still have to reach real numbers. And so Kano gave one possible construction using the decimal representation. But there is one more popular idea. Maybe you can Google about this. It's called a Dedekind cut. Okay, it's a very interesting way of defining real numbers using rational numbers. Okay, and if we get time, we visit that. But otherwise, do read about it from somewhere. Okay, and that's all that I wanted to cover today. So as I said, you can try to solve the remaining problems of this INMO paper, and along with that, I'll also send you some more questions. And as I said, I may not restrict to RMO only. I may take INMO questions also from next time. Okay, thank you. That's all. Bye.
Bye, sir. Thank you, sir.